Hello and welcome to 14th lecture of course on data-enabled tribological engineering from experiments to predictive models. The topic of this lecture is thin film coatings and their tribological properties. We will be covering few features of this topic in lecture 15, which is basically on nanotribology, and few features will be covered in lecture 31, that is the prediction of coating and surface treatment performance. As this lecture is continuation of the lecture 12, 13, so I'm just trying to summarize a few points which we already highlighted in previous lecture. So let me start with learning from previous lectures. We already have defined the wear, which we know that is a loss of the surface material caused by mechanical processes like in the rolling motion also can produce wear debris. Sliding will produce more wear debris, and repeated impact as a fatigue loading can bring some sort of wear debris particles. We have already seen this kind of a picture in earlier lecture. We have highlighted that the wear out of carbon graphite seal. We have also shown in previous lecture also that time when we have indicated the nose of the cam gets worn out, while this was earlier one where we know that change in the velocity which brings a wear from a surface. And this was also shown a kind of abrasive wear, obviously three body abrasive wear in the engine bearings. And we also have covered that if we really successfully implement tribological knowledge in India, we can say roughly 9 to 12 lakh crore per year. However, implementation is not that easy. Reason being, a tribology is very complex. It requires a many discipline knowledge and need to be integrated. And fortunately, we have machine learning artificial intelligence tool where we can really integrate this knowledge, and it will be useful for the future generation. We also mentioned very clearly that many times even the boundary lubrication, or we say we many times we use the word dry lubrication, there will be always some lubricant layer. If we can make a surface better, then even this boundary lubrication layer can be shifted or moved to the electrohydrodynamic lubrication. So what is the meaning of that? If the failure is happening or friction is increasing in this form, we can shift to the this form or this form or this form. That means we can delay deterioration or wear out of the bearings or the tribo surfaces. We can increase the life of those components. We can reduce the friction for the long time. We say in this case particularly, if the friction was up to maybe say 10,000 hours, we can extend to 15,000, 20,000, 25,000 hours at the same level. That's a possibility. That's why we say each bearing in a boundary lubrication is generally coated with some sort of layer. Where even though we use the word earlier, the physical adsorption, and here we can say there's some sort of a semi-solid film or chemically bonded film, which has some energy. And energy, if we are providing excessive energy compared to the bonding energy, then there's a possibility that this layer may come out, may wear out, and that we don't want. That means we want more and more addition. That's why we say ensure bonding and ensure the sufficient energy of the film has been given to the film, obviously that interface, so that coating doesn't come out easily, or this coating or lubricant layer doesn't come out easily. That's very important. And then we say even we provide all the coating, but quite possible there is some surface roughness which can really penetrate this coating, so we need to improve the surface roughness also. So overall, we require a good surface roughness, we require a good lubrication, we really require lubrication not in liquid form, in a solid form also. Now in this lecture we will be learning what a soft lubrication or soft coating related to lubricant. Now we need to also go for kind of hard coating which is related to wear. So overall, we really required a good synergy between lubrication and coating technology. In previous lecture also we say when we go for surface texturing, embedding solid particles or solid lubricant will be very important. So overall win-win situation can be achieved. This diagram also was shown in previous lecture, and what we use the word that service life is a this is a boundary surface life, service time point of view, and then performance not necessary it will be the same level with the time, because of the wear out of the surface it will reduce. So instead of going for the red line, if you are going for the green line, it will be always more useful. If we can really reduce this line, this green line to this dash red line, it will be more useful. And in previous lecture we also learned something like a reuse or reconditioning, repair of the component and reuse. That will bring a more and more sustainability, and it is very important. So we take all the steps together. It's not that only we need to learn only about the liquid lubricant, we need to learn only about solid lubricant, we need to learn only about the repair, but everything is interconnected, and overall we need to take several measures depending on the situation. We also learned from previous lectures that surface roughness, we have mentioned that type 1 surface roughness and type 4 surface roughness, and we said very clearly the coefficient of friction because of that will be different. The not only the surface roughness value but type of the surface roughness. In this case, suppose at the 0.25 we are getting coefficient of friction around 0.18, and here we will be getting around 0.38, 0.4. So coefficient of friction is changing by type of the surface roughness. And what is really required? We really require a negative skewness from a surface roughness point of view. High kurtosis, we are keeping a high kurtosis, reason being because of the interaction and because of the running in period, what will happen, the peaks will wear out, and more cores will be developed, flat surface will be developed, plateaus will be developed, which will bear the load, and then it will enhance the product life. Not only this, valleys which because of the negative skewness, that will act as a lubricant reservoir. So this is also important. Here we are simultaneously synergizing the roughness and liquid lubricant. And then we also define something like a lubricant which is having extremely low shear strength, which we initially drive the relation, and we say any lubricant or any interface having a low shear strength will be very important. Reason being, it will reduce the coefficient of friction, it will increase the efficiency, it will reduce the heat generation, and it will prolong the service life of the mechanical component. Another one we have learned that almost every surface is to some extent contaminated, and that can be even oxide. So it is very good in the sense we don't get any dry case, we always get some sort of boundary lubrication case. Reason being, there is a thin oxide layer which acts as a boundary lubricant, and will this oxide layer will have a shear strength lesser than the parent material, and that will provide a good lubrication. So that's very important for us. Not only this, if that lubricant layer is sheared away, removed, it has also tendency to refurbish its own. So nature is helping us in the way material get some sort of coating, and if it is a worn out, there is a some time delay, and then again the coating will be refurbished. There is always possible to go ahead with optimal lubrication. We can develop algorithm which will minimize the material degradation, overall increase the system efficiency, and that's very important. We also learn one more important thing is that ZDDP, which is used as anti-wear in engine oils, is now facing some challenges. Reason being, it contains a sulfur, it contains a phosphorus, and now the environmental issues are there, and it is restricting the sulfur percentage should not be beyond this percentage, phosphorus should not be beyond this percentage. So there is a challenge for the ZDDP, and we need to really replace in the future engine oil. So for that purpose, some experiments were done by researcher, and what they found, the oil without ZDDP increases the degradation of the sliding engine components. So ZDDP is essential. Unless we get a complete replacement, we will not be able to get a good solution. Here there was a synergy. We were using the lubricant additive in liquid lubricant, and the DDP was forming a boundary layer on asperity levels. So it was really helping to reduce the wear rate. Now, because of the environmental problems, environmental issues, either we need to go ahead with some alternative coating, solid lubricant coating, or maybe hard coating, so that surface do not wear out at all. So there is a need to replace, and now we are talking in these days a nanostructure coating, which has a number of phases that can have a number of properties that also can be made. Of course, those things are still in the research stage. Some more research is really required, or to increase the TRL level, more and more the prototypings are required for that purpose. We also discuss something like a liquid lubricant is very essential, particularly when the two surfaces are loaded and moving related to each other. And so, to provide a smooth sliding with a low friction, we require a liquid lubricant. We give a more importance. Then we give a more importance to the semi-solid lubricant, particularly it doesn't have pumping losses. Now we discuss in lecture 12 a solid substance, and we say any solid substance serving the purpose of the what liquid lubricant is doing can be treated as a solid lubricant. And naturally solid lubricant will require a low shear strength. It cannot be as low as a liquid lubricant, it will be slightly above than that, but because of the high temperature application where the liquid lubricant cannot be used, it get oxidized. Solid lubricant is a solution. So that's why we say that solid lubricant, particularly high temperature situation, or depending on the term and this environmental conditions, it can be utilized. So that's why it requires a low friction coefficient. One more point we were emphasizing earlier, that the wear out. You should not make many dictionary or many books. They say that liquid lubricant is required to minimize the friction. It's not only the friction. More importance is giving a lesser wear rate. So we should also give the wear rate must be within the acceptable limit. We cannot, if any liquid lubricant or any solid lubricant causing the wear rate, that cannot be treated as a lubricant. So we need to make sure that this lubricant is not really harming the surfaces. We also given it's like a multi-functional coating. We say that this coating can be 1 micron, 10 micron, 100 micron. There is an overlay and then the nickel barrier, so that it can be play as an interplayer layer, and the copper material is still backing. So we are going with a multi-layer coating. It's not a single layer coating. So now for that purpose we require better and better technologies, techniques, because earlier the welding, the previous lecture we mentioned about the spring coating, and we discuss about welding, which have naturally the thickness restriction. As far as my knowledge is concerned, many times a spray coating really requires a minimum coating thickness as a 50 micron, while requires a few also. So welding, if we want, actually we need to think about a few When we are going for a spray coating, we need to think about maybe say around 50 or maybe multiple of the 50 micron coating. So we really require better technologies to reduce this thickness, because effectively if coating is getting attached to the surface, we don't really require a thicker coating. And in earlier lecture also we learn, if we go for thicker coating, what will be the problem? Problem will be that it will be the substrate properties will not be utilized fully. So it will be the only the top layer properties. We don't want that. We want even substrate properties should be utilized fully, as well as the top layer friction or wear properties should be utilized. So that's a one point, and another point came that most of the time this solid lubricant which we covered in lecture 12 have a major issue of the self healing, except the soft metal. Soft metal slightly heated, they will bridge the gap, they will flow, and then it will self heal the cracks. But other materials, they do not have this kind of properties. So solid lubricant has one of the restriction. That's why we say combination of a liquid lubricant and solid lubricant can be utilized. Now here the solid lubricant, because it is coming along with the liquid lubricant, it can be few micron thick layer is sufficient. However, we may avoid completely the solid lubricant but we know in between there is a pump failure, or in between there is some peaks which are really coming and trying to penetrate the coating. So that can be easily slided or glided if there is a solid lubricant layer on the surface. So that will really help us. Another one, we see that proper lubrication basically relies on a number of properties, as the surface roughness was pointed out. Now this wear out also depends on the hardness of material, and often it has been realized that when the surfaces are hard, they don't deform plastically, and then they don't really go ahead with junction growth also. So that way the laser lubricant will be sufficient for that purpose. So this is very important to consider when we are going ahead with the tribological knowledge, and we are trying to go ahead with the predictive model. One the paper I'm referring about engineering tribological interfaces, and then how do we improve the boundary lubrication properties. In previous lecture we say the surface texturing, and then is being compared with the super finish operations, because in tribology whatever we do manufacturing, classical manufacturing, we need to go for the super finish operation. Reason being that we really require a lesser surface roughness. Now if I require a surface roughness lesser than 0.4 micron, then what will happen, we really require some sort of grounding, or if we really go ahead with a much better one, like in this case it has been given as a 0.01 micron, we require a polishing in this case. However, surface texture, even though it has some surface roughness, but it is a texture, and because of the texturing, randomness is coming down, and then we have a good pockets where the where debris will be accumulated. It will not cause a three body abrasion, it will not cause additional scratch. That has been compared, and that shows very clearly that coefficient of friction in case of the surface texture, even it may have a high roughness, but it is giving a better results compared to the polished surface, compared to the ground surface. This also raises the question, if I make a surface roughness as a part of the surface texturing, will that be helping? Yeah, it will help, but only then we need to see orientation of the surface roughness. If surface roughness is really made in a proper way, or the grinding is done in a proper way, we may replace the surface texturing. Of course there will be some sort of additional operation will be required, so that is also done by in a literature by a few researchers. So quite possible, and a new surface treatment process will come out, which will give a surface texture surface and lesser surface roughness, and we may get a very low coefficient of friction using that. Now this is a slide I'm again bringing up from a Neil's handbook. While Neil handbook has said there is a possibility of making hard coating. Now hard coating is very common now, almost now more than 30 years these coating have been in the market, and coating thicknesses are roughly 0.2 to 1 micron. So these are the hard coating, and their hardness you can see here something like a 4200. Not only this, their oxidizing temperature is on a higher side. That means this on the at the high temperature, they really show low shear stress, and they can act as a lubricant also, or it will provide a lubricated surface. One more figure has been shown here. We say that without lubricant, if we go hard with the sputtering of MOS2, the solid lubricant, it and then particularly for a complete rolling element bearing all the component have been sputtered MOS2s. That's the molybdenum disulfide. In the situation, they found particularly wear time is increasing significantly. Now you can see here spurred MS2 um, on only race and cage, not a ball, is showing something like a 200 hours, while when going for all the components, it's showing 1000 hours. So using the solid lubricant, or maybe coating in the few micron thick layer on a surface of the tribo components, and then we are going without a lubricant, it really enhances life. But how many places can be done, we need to extract from a literature and come up with the right solution. Now, when we say thin film coating, we say we have many coatings are available and to us, and it's very difficult unless we find which characteristics we really are requiring. And if you see, there are maybe even in 1984, you find that there are so many coatings available. The chemical vapor deposition, etching, ion assisted deposition, ion plating, in this case plasma enhanced CVD, reactive evaporation, the spraying also has a number of method how to spray the coating. So there are many even, and we say that not a single coating can be best for the all application, and not all the coatings are suitable for all kind of materials. So we really required a more detailed knowledge, and covering in this one lecture will not be that easy. So I'm just giving a kind of overview, so that if there's a need, we can explore more and more coating technologies, materials, and then in the application which will be more useful. Let me give an example. One publication in a web, which was in 2022, has come out. It say increasing the wear resistance or railway switches. Now here they are doing with the boron coating. I also did a boron coating long time back. One is a coating, and then it is having a very high hardness, and this high hardness, if it is really done proper way, particularly coating is done properly way, and it is not getting delaminated, then it will show a good performance. So here it's not only the coating, the method, material, but finally the how the surface has been finished, on which a substrate has been finished properly or not, that will also affect the performance. So there are several papers, and every paper you will find somewhat different thing has been achieved. And with the time, even whatever earlier we were saying the coatings were not good coating, maybe say CVD was not performing well everywhere, now it has a plasma assisted coating or plasma enhanced coating. So those features have come. Wherever they find the gap, they are changing and they are improving the that coating methodology, and there's a possibility we may get a better and better coatings. Now you have may have seen this kind of coatings also. We have a polymer surface, and the polymer surface can be plated with a gold, can be with a nickel, copper, or chrome, and we find a different kind of features on that. The only thing comes here that when, because the polymer is a soft surface and we are doing a ceramic coating or we are doing the metallic coating, one is the soft surface should sustain the temperature, and second thing is that the load should not be going beyond limit. Reason being that this coating can be only a few micron, it can sustain some load, but the load increases significantly, then the soft surface will change shape. If the soft surface changes the shape, then this hard coating may break. So there is a need to really make a coating with appropriate load and speed condition. If it is only aesthetic, that's a different thing. Here it appears only the aesthetic is given a more weightage, then is a different thing. But when come to the travelogy, we really require a load and speed conditions also, and we want a minimum to minimum wear rate should occur. So those things are important, particularly when we are going for the coating selection. We say hard coating on a softer substrate can decrease the friction and wear also, particularly from topological point of view. Reason being that it will prevent the plowing effects, because there is some sort of hardness, but again the surface of roughness has to be much lesser than the coating thickness. So those things are important. We need to really account all those aspects. Now, if we come up with coating point of view, we say coating protects the surface by forming the barrier. So, I'm trying to give a slightly different definition. We say it forms a barrier that isolates the material from its degrading environment. We are trying to prevent, give a separation is something like a cover on this the material, and which is giving some sort of barrier between the degrading environment and the material. And overall it is safeguarding in an efficient manner. And then we say whatever we apply a coating, they should have some sort of a characteristics. And what are the characteristics? First thing is that if a 360-degree, and then there should be consistency in a thickness. If it is a 1 micron, it should be 1 micron across, complete on 360-degree. It should not happen some places is a 1.1 micron, or some places a zero point 0.8 micron. So mean value and then a signal to noise ratio we need to really account properly. Another one is that they should not be pores. We will be learning in lecture 16, if there is some sort of crack or there is some sort of pores, then what will happen, there is a chances of tribocorrosion also. If the tribocorrosion, the wear rate initially may be even smaller, but suddenly the component will fail. So we need to keep that in our mind. One is a consistency. There's no consistency, misalignment will be coming there. If there is some sort of pores, then possibility of the and the water getting ingress or getting electrolytic ingress in there, that will be there. Another one is that the coating is not adhering completely, which is a major issue, major problem, that it doesn't get adhere properly because of the manufacturing processes. Then the coating will be removed after some time. Then it is on the very bad. And last one, in this case, we saying that if the coating get punctured, then it should have a autonomous practice or capacity to repair itself. If it is not, then there will be continuous monitoring will be required. And as I in the previous slide I mentioned that we need required then synergizing between the liquid lubricant and solid lubricant. Where the coating get punctured, then maybe the some solid lubricant fill that gap, remove that crack, and give some sort of a strength to the material, so that the degradation can be with the delayed. So we say that to address a tribological issue, what are the tribological issues? We say the low controllable friction. Again, we are saying it's not a zero friction, it's a low controllable friction. Is resistance to the corrosion or resistant to wear. Sometimes we use a word only resistance to wear is sufficient. But however, if there are pores or there are some sort of gaps, and maybe it is not the uniform coating, then corrosion chances also will be there. Then we need to account those also. Another one is that if we want to really choose some sort of coating, we have a many coatings. And then economics will be the one of the major issues, because many coating really require sophisticated manufacturing processes. And if the machine cost is something like very high, expensive, and it is not available in your neighborhood, naturally that kind of coating will be difficult. Another one is what will be the thickness. We also learned earlier that what will be the maximum shear stress which is getting below the surface. If that is known, if it is a 50 micron, naturally we need to keep a coating thickness more than that. That if the maximum shear stress is at a below 50 micron from a surface, then we need to keep a thickness maybe say 75 micron or 100 micron. Another one I say the different materials, because every material may have a different melting point. Like a ceramic will have a high melting point. Naturally, manufacturing processes will change. And what are these manufacturing processes? CVD is one. Chemical vapor deposition, physical vapor deposition is another one. In these days, particularly, more and more research has been done in the PVD side. It is really giving better result, and it is giving very fine coating of even zero point 0.1 or zero point 0.2 micron. That's important. Thermal spray is a widely available, widely used. Even there is a ASM handbook available which is on a thermal spray coating. Sol gel is very easy, and polymer coatings are also easy. They are available technologies and can be utilized for the topological application. Sometimes people use a word of functionally graded material. So instead of the coating, they use a functional graded material, or FGM. I'm just referring one paper on this review of surface modification techniques. Of course, this surface modification which we have explained in the previous lecture, lecture 13, here it is basically referring to the coatings as such. Now they have divided this coating in two form. One say one thin the coating, other one is a thick coating. thick coating, we already know it has been utilized in a manufacturing domain like a powder metallurgy, and for the years and years. Recently, we know that additive manufacturing has changed the manufacturing domain, and more research is being done on that. How do we really refine additive manufacturing? How do we really make a system that everything can be made with additive manufacturing? And then it has been given the complete task of additive manufacturing to the robots also, so that from a material or from wire or maybe the material powder or wire, whole system can be made. However, this is still in a research stage. We don't get a very good utilization of the additive manufacturing, particularly for coating. Of course, it can be utilized in the future. That's why I say technology may change after 5 years. Today, I may select a one coating, say now I am using the word PVD is providing the best result. Quite possible with the more and more technology. After 5 years, additive manufacturing may provide a more better or much better coating also. Centrifugal casting is also well known. Now, particularly spray coating, that can be plasma. Basically, what we are requiring in a coating, that we want to transfer material on a substrate, which generally the 2D polymers or 2D solid lubricant they do. They transfer a layer to the other substrate. So, like I give an example of PTFE earlier. The PTFE, when it is rubbed against the steel, PTFE will transfer a layer on the steel itself, and then it will be the PTFE versus PTFE coefficient of friction. It will not be the coefficient of friction between PTFE and steel. Similarly, carbon graphite against stainless steel. Carbon graphite will transfer a layer on a stainless steel. So, similarly in this case, what we want, we are transferring a layer, but the way solid lubricant we transfer layer, attachment to the substrate is not very good. It is not very firm, and it may be after few sliding cycle, maybe say few hundred sliding cycle, the layers comes out. Then we require the next layer. While coming to the this kind of coating, when we are going for the high energy coating, in this case basically the plasma HVOF, we provide a lot of energy, and when the energy is being provided to particles and they are getting attached to the surface. Now, if we want to remove those particles from a surface, that much energy or maybe more than that energy is really required to separate it. That is the reason that we really embed kind of on the way embed the particle, we transfer the particle in a manner, they make a uniform coating, and then the removal of the coating will not be so easy. So, there is a difference between solid lubricant which transfer the layer, but within a few sliding cycle layer can come out, because the reason being the adhesion with substrate is not very strong. With a little energy, little mechanical energy, it will come out. While this kind of coating really required more energy, high energy to get separated from surface. PVD and CVD, of course, they are done in a vacuum, low pressure, and actually they become a costlier, but they are the best kind of thing. They really make a very good surface, and then controllability is very good. Coming to the electro deposition, electroplating have been used widely in the literature, and we find many surfaces, even electronic component, they are getting electro deposition using copper or gold, this kind of surfaces easily. Now, one of the most commonly used technology in a coating is a spray coating. You must have seen most of the engine part, they get spray coated like that even in the markets. But what is the problem? You can see here this kind of paint which comes into the environment. It is really harmful for the environment. So again, it has to be done in a closed chamber. Not only that, in closed chamber, whatever the paint which is getting wasted, either it should get recirculated, otherwise if it is a waste, then it is a sustainable issue will come in the future. What we do in this case particularly, we use the thermal energy or heat energy to melt materials in maybe say in semi-solid form or the liquid form, and then we give a lot of acceleration. So this is what we say in the in-flight particles. and there is a substrate, and then we directly impinge on the surface itself, and we get a few micron, or maybe say 50 micron layer thickness in one go. If you and then this substrate can move up and can move down, depends on the whether we are using the CNC machine or using some sort of other fixture mechanism, and then we can really cover more surface also. So I can say that this thermal spray coating is a very fast process. We can change and cover the surfaces very fast compared to PVD and CVD, but it has environmental issues. As I mentioned earlier, there is a separate ASM handbook on a thermal spray coating. If you have interest, you can read this. I'll just try to summarize. I say engineering material in this case can be plastic, it can be metal, can be composite, can be ceramics, or some sort of alloy. Even it can be used in the form of the rod, in the powder or wire. Main thing is that they need to have a flowability. It can be partially melted or fully melted, but it need to have flowability. And then they pass through the heat source. It can be plasma, even it can be electric current, or sometime we use a combustion also, chemical combustion, to give energy to the particles, so that they go with high velocity and directly hit the substrate. The thermal spray can produce a coating from 20 micron to few mm. We have one facility in our lab, but we are not able to produce better than 50 micron. So minimum 50 micron thickness layer is really required. If I go ahead with the minimum 50 micron, I can go ahead the multiple of 50 micron, 50 micron, 100 micron, 150 micron, and move the component in the manner. But lesser than 50 micron, we are not able to deposit. Another good point about this technique is that it's a high deposition rate. The deposit, and even we give a velocity, very high velocity in this case, and then we find the droplet size in very smaller size, as say 20 micron, 30 micron, or lesser than that. That's why we are able to get this kind of coating thickness. So it's a very fast, widely used. Most of the equipments are available in the market, but it will cause environmental pollution. So it has to be done in a closed chamber, and whatever the paint may be, assuming that 10%, 20%, 30% powder has been utilized successfully, but other powder has been is going waste. So how do we really go with a sustainability issue? The reason being, we want a near net manufacturing kind of thing. Whatever that I'm using, whatever the powder I'm using, it should be used 100%. From that point of view, I believe the spray coating may not be giving very good solution. However, other coating solution also we need to evaluate. Quite possible in other coating also we are not getting that kind of good result. However, I know the electroplating we get a good solution, and can we utilize the solutions also. Now coming to the this spray coating which I mentioned, here we can give any form of the energy. Coating materials, as I mentioned, that we can give in powder form, we are giving in a powder form. It can be wire form, it can be even the rod form. And then we use some sort of gas, compressed gas, so that this kind of the flow comes out. And there is a substrate and there is a coating, as I mentioned, that if you want to cover this complete sheet, naturally it has to move down to get covered, and it has to move up to get covered. So this is what we are showing, something like a high velocity oxygen fuel spray coating. Even though it was invented in 1958, but it became a commercially available in 1980. After that, the problem was found in the design of the gun. So again, they improved the design of the gun. So whatever the technology which is developed in a lab, it takes almost 50 years to come in a successful win market. So whatever we are reading in a publication, quite possible it will take little longer time to come to the market and then become a commercially available. So whatever coating we select, it should be based on availability either in our laboratory or nearby, or should be available to the vendors who are buying the machines. Now here it has been shown that substrate coating is really impinged, and then if the surface is a rough surface, we have found the deposition of coating will be better. Reason being, the rough surface will give a good results compared to the smooth surface. So that's why many times the surfaces are roughened, before the coating purpose. That's also important to consider. Now we are continuing with the same. We say the how do we prepare the surface. We say basically we do a grid blastings and blasting or kind of thing. You can see here it was a smooth surface, it has been made a rough surface. So this is important. For tribological purpose, whatever the we get manufactured surface, we generally do polishing. Now instead of that, if we directly come to the coating and a 1 micron, 2 micron, 5 micron coating, and that gives a good surface roughness, that will be always a better option or desirable option. So instead of going for the surface first polishing and then going for surface texturing, if we have a surface which is a rough surface and we directly go for the coating and a few micron, depends on the what kind of course we need to really write a right code to evaluate what should be the coating thickness as such. That can be done. Here we are sending oxygen and fuel, and then powder, we are as a, we are making in a ball mill the powder, we run it for the different hours and compress gas, and finally we get this kind of coating on that. As mentioned in our lab, we get up to 50 micron. 50 micron is one go. If we want 100 micron, 150 micron, then we need to go for the reciprocation motion also. Here in our case, what we are using, we use aluminum powder, and then we use a temperature for aluminum is around 2000 degree. If you want to go for the ceramic, we go ahead with 3000 to 3500 temperature. So in this case, temperature input is on the higher side. It is a liquefy, or then we use a compressed gas so that fine droplets are made, and those go and get impinged on the surface. And we have also found the porosity can be controlled if we go for finer and finer powders. So if it's 5 hours ball milling, if I go for 15-hour ball milling, coating which will come, porosity will be lesser and the surface will be better in that case. I'm just showing you one of the coating technology which was developed in one of the lab, and then it was developed from additive manufacturing point of view, and this is the nozzle design was done, and what they have used a laser. So instead of the temperature or thermal heating, or maybe say combustion point, here the laser has been utilized for that purpose. And then this table has been given scanning direction. Here the table has been given motion in this to this direction, and better has been shown in this case. Powder comes from this kind of tunnel, and then here the laser is developed. So whatever the powder comes on the interface, and the laser will make a immediate action, it will melt it so that can get deposited. Again, as I mentioned, the scanning direction need to be controlled precisely, and then the laser continuity also should be there, powder supply also should be there. The only difference here is that we can use a different kind of powders. So it is not only the aluminum powder, it's not only the ceramic powder, we can mix number of powders and we can supply to the surface. However, as I mentioned that what is the powder size and all depends on the coating thickness. Now if we are able to make a 50 micron coating in one go, naturally if we want to go for better, we need to reduce the powder size, and then maybe say, the strength of the laser also, so that melting is easier. Otherwise the substrate itself will get melted, then it will not be really very useful, it will give unnecessary in the deformed surface. Another technique which has been used is the chemical vapor deposition. It has been shown in sketch form. In this case, what we do, we get a gas of the surface material which need to be deposited on a substrate, and substrate is heated, of course, under the low pressure, or maybe say vacuum kind of, almost a low pressure kind of the vacuum, and gas is really moved out in this manner. Now if then it is not utilized fully, then it has to be done something to recycle it, otherwise it will be causing environmental pollution. We say CVD is suitable for the ceramic and metallic components, and then it in this case particularly deposition is generally done in the gaseous phase. Now here is the important that we can do a number of experiment by manipulating conditions, something like a base material can be changed, temperature can be changed, gas mixture configuration can be changed, and then we using the gas flow and the pressure also, that we can really develop a different kind of properties of the material. So this is where very important. It's not the ones there is a only one CVD process and it will give always a similar kind of coating. When you change parameters, then the different kind of coating will come out, and that's very important. However, this coating technology has also limitation. One is a chamber is a restricted. I in this case particularly look at that. I'm keeping a surface here. Now ideally it should be the 360-degree where inner surface, outer surface, they need to be coated, then it's okay. But if it is only 10% of the chamber is being used for the substrate, naturally that there is will be more losses. So what we see here, the limitation is that one is that we are heating the surface, so that substrate need to handle that high temperature which we are providing. Another one is a vacuum in this case, and last one is the wastage of the material, coating material. Either we do something to so that the gas which is coming out here, material coming out along with the gas can be recycled, can be reused. If it is not, and there is assuming that when this route this material is getting oxidized because the vacuum is being developed only on here, and this surface, if it is not completely vacuumed, or maybe there is some sort of oxygen ingress, then there is a possibility of oxidization because material is getting going for the high temperature, and then that material go completely waste and we need to discard. So wastage of coating is possible, and then material should be subjected to the low pressure and high temperature. These points, if they are satisfying, then we can go for CVD. Electroplating, as I mentioned, it has been utilized for the years, and what we do in this case, basically we use a table and we figure out which has an anodic nature and which has a cathodic nature. Naturally, the anodic nature will always be subjected to corrosion, it will lose ions, and then when the loss of the ion, and the other surface will get those ions. In this case, suppose if there is a copper and copper comes on the higher side and the aluminum comes on the lower side, naturally in this case aluminum will be losing the material and copper can gain, or maybe there is some other material which where we really require deposition, it will gain the material. However, this can be explained in a lecture 16, which lecture 16 is on the tribocorrosion. We will be discussing about what is this electroplating or electrodeposition or corrosion action. So basically I believe that this is the kind of corrosive action which is a negative, but people are utilizing from a manufacturing point of view is a positive from that angle. So what is electrochemical method? Produces a uniform layer, you can see here, because it is covered with a complete solution, naturally it will have a better uniformity in the layer. And only thing is that the material need to be conductive, because we are supplying electric current, and if it is not conductive, it doesn't absorb the electron, naturally it cannot be utilized for this kind of process. We say when we insert it into electrochemical unit cell, a specific material are selected to function as a cathode and anode. And the cathode and anode, as I say, that these are the materials which go have a cathodic nature, and these are the material which have anodic nature. Again, they need to be compared, like iron versus tin. Now in this case iron will work as a anode, and tin, if I combine with that, the tin will work as a cathode. So this is a very important, what is the electro potential difference between two material. Well, however, this can be discussed in the lecture 16. Physical vapor deposition technique has been used extensively. Now earlier we were using only the crucible to heat the material surface. Is the same restriction what we use in the CVD, same restriction here. However, to give much more high temperature, either we use electron guns also. Now we say that most of the material they can sustain a temperature up to 1500, and maybe say they get a vaporize and then at the 1500, but some material oxide they don't get a vaporize at the 1500, then we may require electron gun to increase the temperature. So we have option crucible is a one, electron gun and the both the side, and then we need to again maintain the vacuum in this case. and this is a substrate where the this the atoms or particles will go and impinge with a velocity, and then it will get deposited on the surface. However, there are number of corners. Again, the powder which is the left here, it will get also accumulated in this manner. So that's why many times we don't want that kind of the loss of the material. We give some direction. The material goes only in this direction, is a focused. So that is also possible. So what we can say here in this case, utilize process of vaporization to transfer material at atomic level in a vacuum environment. In this case, we are going for finer and finer coating. PVD techniques differ compared to the CVD because it utilizes a solid. In this case, the material is a solid. We are not passing the gas form and the vacuum. However, PVD also can be made for the gas form. But here we are showing as a solid form. That from that point of view, I am showing that it is mostly utilized as a solid precursors, while CVD involves only the gases. In PVD we have options, well CVD has only the gases. In another one is we are able to go ahead with thin film deposition, and what we say, it can have aesthetic good features also. It has a good resistance to corrosion and wear, and more research is done in this form. uh, there are some there are some publication where they have already done this coating on engine components. So I'm just showing here for piston ring. When the piston ring are made of the steel, chromium nitride has been done. When the piston are made of the cast iron, the molybdenum disulfide, titanium nitride has been done. Steel chromium nitride, again nitride is steel chromium nitride has been done. When the piston which is made of in this case aluminum and silica percentage is kept on a higher side, that can we have also a MON coating and a titanium nitride coating. Piston pin again made of the aluminum, they are using DLC coating. So DLC is one of the very important coating. To some extent we cover in this, and some DLC will be covered in the next lecture, lecture 15 on the nanotribology. Cylinder which is made of the cast iron, in this case the chromium nitride again, bearings zirconia nitride, gears also have a coating. So PVD has been applied in all engine components, reason being now it is getting more and more popular. Now his coating performance is evaluated, needs to be evaluated, particularly what is the morphology of a structure. If there is some sort of discontinuity, need to be improved. What is the hardness, what is the elasticity, what is the shear strength particularly in the surface, and adhesive strength, friction and wear characteristics. And now particularly for engine component, because they are subjected to high temperature, corrosion property becomes a very important. So and somewhat those things will be covered in the lecture 16. We say the PVD, we are doing evaporation, but to focus, to go for the high energy, we can also use some sputtering approaches also, so that can give a better results to us. I'm just showing a few Indian component which have been done a PVD coating, and that they have mentioned the coating thickness varying from 0.1 micron to 50 micron, and there are important aspects has been mentioned in this case. Due to detachment, delamination, cracking and spalling of the coating material, this coating may fail abruptly. That's why they are using the PVD, because PVD has much more energy. As I mentioned, that sputtering is for again focusing, that we provide a better energy to the materials, so that they impinge and then they remain firmly on the place where we are putting it. So coating hardness is a crucial parameter, coating toughness is the crucial parameter, and adherence to the surface. Maybe in next lecture we will say how do we find out that what is the coating thickness and what is the strength of the coating on the surface, where how it is getting adhered. Those things will be covered in next lecture. And next one is a smooth topography to avoid the, because we have already learned that peaks and valleys are lesser, then the surface stresses will be lesser and contact stress will be lesser, and those can be done particularly when we are working on atomic level. Surface roughness can be improved significantly. Sometimes we require a high thermal conductivity, particularly in EV vehicles. In this case, Those things are important, where the electric conductivity will be very important. Sometimes we require a very low chemical activity, we want corrosion resistance, that is also we have a requirement from a coating. So these are the important aspects, particularly when they consider for the engine case. Now coming back to the PVD, we mentioned about two approaches, evaporation approach and sputtering approach. We see the in evaporation approach, and then when we are comparing with the plasma, or maybe we are comparing with the thermal spray coating, that will be very fast compared to evaporation coating. That's not easy to compare. Other one is, as I mentioned, that up to 1500 degree it may not really require electron beam evaporation, but if on the high temperature we really require. Another one, in this case particularly, adherence of the quality on the surface is very good if and we are going for the high energy. However, at the low energy, particularly when it is only crucible related, they have found that the adherence will not be good. So that's why we are moving to the sputting coating, or we are going with a more beam coating on that. Of course, for that purpose, we require advanced on the evaporation processes, utilizing also plasma, because plasma is the fourth state after the gas, and then that stage naturally energy level will be on the higher side. So particle that evaporate and pass through the plasma zone become ionized and can generate a more concentrated film. That's what they are using the word that advanced evaporation process should be utilized. Plasma driven electron beam evaporation is optimal method. Again, it is on the research stage, and people who are utilizing commercial level is basically for the glasses, to make an anti-reflective coating on the lenses and optical eyewears. Coming to the sputtering coating, we say that in this case we are trying to control the particles movement or atom movements, and the analogy of the particularly can be given as billiard games, where we have a stick and then we direct the balls. So similarly, there is a stick and they are trying to direct the balls in the right place, that where it should come, and then and go for the densification of the coating. And again, in this case, and the different gases have been utilized. First case in this case has been mentioned as the argon, where argon has been getting the positive ions as such, and it gives a direction, and then and the moves this emitted atoms directly, so that it can go and form the layer on the substrate. If there are some other form, like nitrogen is used for the nitrides and oxygen is used for the metal oxide, so in not only the argon but other gases also can be utilized to further better results. Now finally comes to the what are the trends. Now trends are coming that we really require a low coefficient of friction, and then for that purpose in this day the DLC has been giving excellent results, and more coating are coming from a DLC, because it is carbonous material also and doesn't harm the environment. This has been shown for the nanostructure, and I am referring the paper of the review paper on engineering tribology interface, that was published in 2005. It's a nanostructure coating has been mentioned in this case. Reason being, this coating has a many metallic and many ceramic phases over the thickness. That needs to be optimized what we want, how much material, how much ceramic, and what are the different phases, and it's shown that the coefficient of friction is continuously decreasing with the time. So it is getting adjusted, and then the more and more the better and better results are happening. We say the coating must passes, and then it has some functions. It has a high hardness, extremely high hardness of this coating, nanostructure coatings. Reduces the friction has been shown here, and that can operate at a elevated temperature, high temperature. So that will not be a major issue in this case. As I earlier mentioned that this plasma assisted the PVD coating is really methodology is required for this kind of coatings. Now here we are talking not in a micron level, we are talking about the 50 nanometer in the level, and the hardness is somewhat the 40 to 60 gigapascal. Coefficient of friction can be the particularly when we are going for this lower level is a 0.03 to 0.07 also, and it has been estimated that it can really replace the ZADP or molybdenum, wherever the sulfur compound is coming, or phosphorus compound is coming, they can replace this and then this kind of coating can replace those options. Sometime we choose because we say the many properties, we expect that there should be some property that it should be available industrial point of view. What it should be cost economic, should be having operational simplicity, should have a lesser surface roughness, range of the porosity. So for that purpose people use a spider or radar chart to select the which coating will be fruitful and which coating will be really useful for them. However, we go slightly different method. We say we are working on engineering mathematics point of view. So we use a coating selection method slightly different manner. We say that coating system tribological response depends on several variables. What are the coating properties? What are the counterparts, substrates, and different conditions. Another thing is that keep on newer materials coming, newer methods are coming, and wherever the gaps come, people try to modify. Maybe after 10 years, that whatever was a major issue of the one coatings and the methodology, that has been overcome. So those things will come. So naturally we really required the very good engineering method, and for that purpose I am recommending the weighted objective method, which can be used for the coating selection method. So I will illustrate one example for that purpose. We say that we choose some properties of the materials. It can be hardness, it can be elasticity, it can be cost, or some other thing, and we try to choose the weightage of the property. If I go with this figure, almost all the properties have given us same weightage, but in reality it may not be the right thing. So we require a different weightage. And how do we go for the different weightage? This is what we say that enormous literature, enormous data are available in literature, and then we can choose PVD, PA, PVD, CVD, CPS, CVD, and implantation, so and the sol gel, electroplating, laser. There are many techniques available, and then with the properties also. So we really require a good method to choose right thing. So I have selected and the one example, as I mentioned here, we are saying we require a hard coating which have a high hardness, high Young's modulus, low thermal conductivity. Now look at the two contractics. Few parameter we require higher level, few parameter we require lower level, and then low expense. So for time being we are using only the 4 parameters. It can be 100. For mathematics there is no problem. Once we made an algorithm it will be useful. So for time being we are choosing 5 coating: DLC, SiC, titanium carbide, aluminum oxide, or zirconia oxide. We are choosing 5. Again, if I go for the DLC itself will have 100 coatings. So we, for time being, just to illustrate purpose, I am taking this example. Now these are the values being given to us. First thing that these values need to be compared, and then we need to compare the properties also. Which property is more important? Is it the hardness more important compared to Young's modulus, or Young's modulus is more important to compare to thermal expansion, or cost is more important compared to thermal expansion? So those things we need to really give weightage, appropriate weightage. So that's why we say step 2 is determining the relative weight of the properties by comparing pair of the properties against one each other. So we have then the 4 modulus, in this case hardness, Young's modulus, thermal expansion, and cost. And then when we compare here, we say we are comparing first hardness versus Young's modulus. Second, we are comparing hardness versus thermal expansion. Third one, we are comparing hardness versus the cost. And fourth one, because we don't want any property will be removed from a surface, so we are bringing some sort of a dummy variable. Dummy will always get a 0, so it will not be utilized. But suppose if I don't include, one of the property may get a 0 value, so it will be not a good practice. So that's why we are providing a dummy here. So in this case, hardness with our dummy 1 0. Now this has been mentioned, 1 means it is more important and 0 means it is not that important. So that's why we are using the word digit logic method. Coming to the Young's modulus versus thermal expansion, we say thermal expansion is more important compared to Young's modulus. And again, the Young's modulus comparison, cost is more important. Coming to the Young's modulus versus the dummy, we find that Young's modulus will be important because dummy is not that important. Coming to thermal expansion versus cost, we say thermal expansion is a lesser given weightage compared to the cost. Coming to the thermal expansion versus cost is a 1-0. Naturally, the last one is only the cost. So this is what we can do in this manner, and then we get an overall the summation. So here we in this column, so 1 plus 1 plus 1 plus 1 is makes a 4. That's why the 4 has been given here. Young's modulus 0 plus 0 plus 0 plus 1, it has been given 1. Thermal expansion 0 plus 1 plus 0 plus 1, it has been given 2. Coming to the cost, 0 plus 1 plus 1 plus 1, it has been 3. We sum up and normalized. Say 4 divided by 10 comes to 0.4, 1 divided by 10 comes to 0.1, 2 divided by 10 0.2, 0.3. So these are the relative weightage given to the property. That means in this case, hardness has given highest importance, the cost is the second importance, thermal expansion third importance, and then last one is a Young's modulus. It may vary from one example to another example. Now next one is that how do we compare the different things, like we have a hardness, we have a cost, we have thermal expansion. Either we do normalization or we use some sort of a utility score. Utility score, basically we give marks from 1 to 10, or sorry 0 to 10. 0 means totally useless, 10 means the best, we don't have more than that. So just to compare that purpose, we for time being, I'm assuming that we don't have a worst material and we don't have a best material. So that's why I've used the word 0.9 instead of 1, and instead of 1 I have used a 1.1. That means whatever the value, we are getting best value for time being. There's a possibility that 10% improvement is in future will happen because research is going to improve the solution. Next one is that minimum, because we will try more and more trials, quite possible 10% decrement is also possible. So this has been done. Now let's see the DLC has an 8000 hardness, SiC has a 2600, TiC 2800, aluminum oxide to 100, zirconium oxide 1200. Now we need to compare it, and then how the comparison comes out using this formula. The DLC, even though the best 8000, it is getting only 8.96 number. That means still some better coating is possible. That's what we are using. If I don't use, if I use this as a 1 and this is a 1 and this is a 1, then I'll get a 10 number here. So in that situation I'll get a 10 here and I'll get a 0 here. Both are not right. In my view, that future there is some different thing is possible. So I will not use a 10, I will not use a 0, both the cases. In this case, next one is a 2600, we are getting 1.97, and the TiC we get a 2800, here we are getting 2.23, and in this 2100 we are getting 1.32. So this is a utility score of first parameter hardness. If I go with the same way, Young's modulus, similar comparison than what we are getting here DLC, because here the Young's modulus is something 901, which is the highest one, and zirconium oxide has a minimum one. So here I am getting 0.23 and here I am getting 8.9. SiC is 3.72, 3.6 and 2.76. So these are the same, whatever the relative ranking you can compare, you find the similar manner. Now third one, here we record a lesser thermal expansion. So this is a negative side. So for that purpose we use a utility score as a 10 minus this score. Here we want to subtract that whatever say. So here in this case utility score is thermal expansion is we required minimum. So here we find a DLC has a minimum thermal expansion and zirconium oxide has a maximum thermal expansion. That's why, because it has a maximum thermal expansion, that's why it is getting lowest number. The DLC has a minimum thermal expansion, that's why it's getting highest number. SiC has a in between 5.3 to 6.3, it has a slightly higher side, so 3.39, and this will be 3.30. So everything is matching from that point of view. Last parameter is the cost. Again we record a minimum cost, and the DLC has a maximum cost. Naturally it will get a lower number, in this case it is 2.09, SiC is getting 4.88. This is slightly on higher side, so 4.18. Aluminum oxide is slightly lesser, 5.57. This is the lowest one, that's why it is getting 8.56. Now this is done. Now we got a utility score and we got a weighting factor. Now we need to find out the overall ranking. So whatever the utility score into weighting factor, 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 overall score comes out with 7.1. SiC same thing, utility score into the weighting factor. You can see here all are the 0.4s. In this case you can see all the 0.4, then 0.1 second parameter, third parameter 0.2, third parameter the cost is a 0.3. Based on that we can say 1.1, 3.8, 3.2, 3.1. So here the continuous, we can find this is a completely different separate 7.1. Naturally this is the best material for our purpose whatever we selected. So this kind of algorithm can be devised and we can choose right materials. However, suppose we have some other materials and one says the 7.1, other point says the 7.3, other one says that 7.5, and last one says the 6.9. Naturally I will not choose one material because there is already some subjectivity. I may choose all four material and do experiment in my lab to come up with the right results. So what we are saying here, we are trying to extract the material from a literature so that which material will be giving the best results to me, and then I go ahead based on that. So that is what we say the data driven approach. We are collecting data from literature, we are utilizing our knowledge first and trying to choose the right material. In future it will be data driven approach. In the situation whatever comes in situ in the data from a sensors, that will decide the how to approach, that will be coming out. Initially is our intelligence, and future maybe say lecture 23rd onward we will bring a more like artificial intelligence. The data will decide what is to be done. Initially we are imparting our knowledge, we have a texted knowledge, so we are imparting knowledge, we are developing algorithm. Future program should be that software itself generates everything and then decide on that. With this I say thank you for attending this lecture. Thank you.